General relativity, step by step. I've been looking at the linearized Einstein field equations, and I've been considering two objects here, fish tanks, in free fall, and they're at rest in their coordinate system, and they're also at rest in the sense that they are at free fall, in free fall. They're elevator frames. And I showed that even though they were at rest, the distance, the proper distance between the two, was oscillating in response to the passage of the gravitational wave. What I want to do now is I want to talk about something which is kind of obvious, but I think it needs spelling out because nobody told me this, and it would have cleared up a lot of confusion for me. I'm just going to take one of these fish tanks here. There it is, fish tank, and I'm going to consider its world line. And we know that its world line is just t, x, y and z. And these three spatial components, they are unchanged. So I'm just going to call it t, x0, y0, z0. I'm just going to pinch in a little bit. So here's my world line, and I'm going to pick it two times, t1 and t2, for an event e1 and e2. And I'm going to ask, what is the proper time separating these two events? Separating these two events. That's a non-trivial question, but we'll see what happens. It's a piece of magic, this, I think. Nobody told me this. So the metric tensor mu nu, and we've chosen a very, very specific coordinate frame in which it's the sum of the Minkowski flat space metric plus something small and oscillatory. So it's equal to -1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That's that bit there. Plus something small times a tensor in a very particular form, which has got alpha, beta, it's symmetric, so these two terms match, and it's got no trace, so that's 0. E to the I, this is the oscillatory component, minus omega, I took it to be minus omega t plus omega z. And that was the simplest form we could possibly take it. So we're asking, what is the proper time separating these two events here, E1 and E2, in this particular, with this particular metric tensor? Well, tau, the proper time, that's the proper time. Even now I call it wristwatch time. Wristwatch. Is that how you spell wristwatch? Wristwatch time. It looks wrong. Oh, it's because I've got an extra T there. Wristwatch time. Equals the integral from event 1 to event 2 along the path of the square root of minus g alpha beta dx alpha dx beta. And we've got to use calculus to find that out. I'll just neaten that up a bit. I'll pinch in a little bit. It'll help me write better. Here we go. dx alpha dx beta. Didn't make much difference to my writing, did it? Let's try that again. X beta. I'm having difficulty with my interface. dx x beta. Okay. Along with the path from t1 x0 y0 z0 to t2 x0 y0 z0 because these three spatial components are unchanged because the object is at rest in its own coordinate system that we have very carefully set up. So that tells me that dt, well, we'll come back to that, dx equals dy equals dz equals 0. And so this term in here, g alpha beta dx alpha dx beta, if alpha is not equal to 0 or beta is not equal to 0, that means that we can ignore those terms. And so what have we got left out of this thing here? We've got g0 0 dx 0 dx 0, which is just, oh, I'm sorry, there's a minus sign, 0 0 dt dt. So let's go back to what we're trying to do. We're going to have the integral from event 1 to event 2 this is proper time tau, which equals the square root of minus g00 dt, and I may as well just write dt squared, equals the integral from event 1 to event 2 of the square root of minus g00 dt. And you'll remember that the events I've chosen are indexed by t1 and t2 along the world line of the fish tank here, so I can just substitute for that. Well, hang on a minute. Let's do it absolutely step at a time. Integral from e1 to e2 of the square root of g00. Now, you'll see from the formula that I wrote down here that g00, which is the top left component, is just minus 1 plus nothing. So g00, I'll write it here, g00 equals minus 1 to first order at least. Okay, so I can just substitute that in here. Just a minute. Square root of minus 1 dt. Oops. Oh, it drives me nuts. It drives me nuts when this happens. Got all this algebra here. On and on and on. Okay, equals the integral from e1 to e2 of just 1 times dt equals the integral from t equals t1 to t2 of dt, just pinch in a little bit, equals t2 minus t1. Well, that was quite a lot of work. Let me rephrase. Let me go through the whole of this process again. Here's my fish tank. That's space in some sense, and this is time. Here's my fish tank. There she is in the fish, and she's got a world line here in free fall, a free fall world line, and there she is at time t1, and here she is at t2, and the proper time tau equals t2 minus t1. So what that tells me is that the coordinate time t, coordinate t in this very peculiar and special coordinate frame that we've chosen, marks off proper time for a fish. So, but the problem is, well, it's not the problem, but the beauty of this system is that coordinate time t is common to everyone. Everyone uses t. Every fish. There might be another fish here and another fish here. There might be lots of fish, all with their own separate world lines. Every fish in free fall, at least, uses t. So therefore, every fish ticks off time. No, let me write it out precisely. Every fish, I'm not doing very well deleting these, here we go. Every fish has the same tau, the same proper time, as every other fish. Because every fish, you could put other animals in there if you like. You could put any animals, mollusks, anything. Every fish measures tau equals t1 minus t2. Because the argument I've mentioned is not specific to any particular world line. So every fish has the same proper time. So there's no time dilation. There is no time dilation, at least at first order. In a gravitational wave. All right. That may not sound very surprising, but what it means is that we can dispense with any notion that time is varying as objects sit there with a gravitational wave passing them. Compare a black hole. Now here we had an entirely different metric. It was equal to, let me get this right, it's minus 1 over r dt squared plus dr squared over 1 minus 1 over r plus r squared d omega squared, where this is the angular velocity, angular components, and so on and so on. So that tells me that in the same situation, d tau equals dt times the square root of 1 minus 1 over r. Here I'm using units in which 2gm equals 1. That's why you might see this equation in a more complicated, unnecessarily I might add, complicated form. So if we choose r equals 2, for example, so there's the black hole, there's the Schwarzschild radius, and we're considering that's r equals 1 is the event horizon, that's r equals 2 here. That says that d tau equals dt times the square root of a half, which is about 0.7071 dt. So, and of course, this depends on, well, it doesn't, yeah, I've just chosen a particular radius. This depends on r. So what that says is that different, well, let me write it down in its original form, equals dt square root of 1 minus 1 over r. This says that different observers measure different amounts of proper time according to this factor here, the square root of 1 minus 1 over r. Different observers measure different amounts of proper time. Proper time for the same change in coordinate time. So different observers experience different time dilation effects. And this does not occur, this phenomenon does not occur in gravitational waves. Why? Well, because I've just gone through this whole very complicated, pointless in a way, but all I've shown is that the proper time as measured by any particular observer at rest, the proper time measured by any observer is the same in a gravitational wave to first order, and that is not the case in the black hole. So gravitational waves from that perspective are a lot easier than black holes because you don't need to worry about time dilation. Everybody can use coordinate time. And everybody's motion looks simple. Stop. Stop there. Nobody told me this. I had to figure this out. Stop.